All right, chemistry, let's start this combined section. Chapter 5, sections 1 and 2. Here we go. We're talking about the periodic table. We're going to start with the history of the periodic table before we start talking about the table itself. What I'm wanting you to be able to do at the end of this lecture, explain the roles of Mendeleev and Moseley in the development of the periodic table. Then describe the modern periodic table. Okay, that infers that the periodic table as it is today is not always as it's been. Then explain how the periodic law can be used to predict the physical and chemical properties of elements. And lastly, describe how the elements belonging to a group on the periodic table are interrelated in terms of atomic number. All right, let's get started. Now, like we said, the periodic table as it exists today has not always been the case. In fact, there wasn't always even a periodic table per se. There were simple, odd groupings of elements based on similar chemical characteristics. If they tended to react in similar ways, they were grouped together. For example, one of the earlier systems of grouping elements based on their chemical properties was known as triads. So we'd have similar chemical properties, but we'd see the physical properties, things like mass or density, they varied in a very orderly way according to their atomic masses. So enter Dmitry Mendeleev, or Mendeleev, however you want to say it. He was the first one to actually put these elements into what we would now refer to as a periodic table. Now it's a table because it's a table of data. We call it the periodic table because the information and the characteristics repeat every so often. That's what it means to be periodic. Okay, so a periodic table, and this is one of this is one of Dmitry Mendeleev's periodic tables, circa 1872. Okay, but you can see here if you look at these different little blank areas within the table, these represent elements that Mendeleev deduced existed but were unknown at the time because they hadn't been discovered yet. Okay, and that's actually an amazing decision in and of itself. Hopefully we'll get a chance to talk about that later. But this is very, very early on, and several of the elements that are known today were not known at this time. Now, what Mendeleev did at first is that he realized that the chemical and physical properties of the elements repeated in an orderly way, periodically. Okay, they would repeat periodically. And this would happen when he would organize the elements according to increasing atomic mass. Now, if you are listening very, very closely and you're remembering things that we've talked about in previous sections, that should ring a little weird for you because we learned that the periodic table is arranged according to atomic number. Okay, and Mendeleev did not arrange his periodic table in that way. He arranged it in terms of increasing atomic mass, and I'll tell you why. Because there was no way to determine atomic number at this time. That technology had not been developed yet. So the best they could do was use masses. And so they did. In 1869, Mendeleev published a table of the elements organized by increasing atomic mass. Now, Mendeleev was a Russian scientist and is often referred to as the father of the periodic table because at this time, other scientists were working on creating things like Mendeleev's periodic table. The only difference is that Mendeleev's data was impeccable. It was the most well-organized, well-known, well-established data, well-organized data out of anyone who was trying to put together this type of table. Now, this idea of repeating chemical characteristics, okay, is called periodicity. Periodicity is the tendency to recur at regular intervals. Just like a newspaper used to be called a periodical. Why? Because it would come out periodically, most of the time, every day. Okay? When you have a period in school, that's because that is a chunk of the school day that occurs at regular intervals. And you guys are very used to that school schedule. But that's periodicity. Now, the chemical properties of the elements are periodic functions of their atomic weights. That's what Mendeleev said. That's the fundamental, foundational idea behind his periodic table. The chemical properties of the elements are periodic, meaning repeating, functions of their atomic weight. So that means that they're dependent on their atomic weights. Again, Mendeleev had no way to actually count the number of protons in a nucleus. He had no way to count the number of positive charges in that nucleus at all. So the best he could do was atomic weights. And for the most part, it was pretty darn accurate. Now, Mendeleev made some exceptions, okay, to place elements in rows with similar properties. There were a couple exceptions, things that didn't quite work. Elements like tellurium and iodine, they were switched on his periodic table, because if you actually look at tellurium and iodine on the periodic table, they're going to be down and to the right, numbers 52 and 53. Now, tellurium is number 52, and iodine is number 53, but tellurium has a larger average atomic mass than iodine, about 127.6 compared to 126.9. And so because Mendeleev was arranging his periodic table in terms of increasing atomic mass, he actually listed iodine before tellurium. Now, there are missing elements, okay? Gaps existed in Mendeleev's table because Mendeleev predicted the properties of the yet-to-be-discovered elements. Things that he was able to predict and that were not discovered yet, but then were later discovered: scandium, germanium, and gallium, to name a couple. But he realized that there must be elements to fit in these areas so that that periodicity could be perfect, and so he simply left gaps, assuming that an element would be discovered that would be placed there sometime in the future. So we have two names we're going to get started here. Horizontal rows. They all have similar chemical characteristics. Okay. Vertical columns are in order of atomic weight. I want to give you names for the horizontal rows. Those are called periods. Periods are horizontal rows. Periods. Vertical columns are called groups. Sometimes called families. We call them groups. All right. So if I'm talking about a horizontal row, I'll say period. If I'm talking about a vertical column, I'll say group. Now, Mendeleev's table was not perfect. Okay. There were some ideas like why didn't some elements fit in order of atomic mass? Like why when we look at tellurium and iodine, why do they not fit like that? What's the deal? They seem to be backwards in our modern periodic table if the atomic mass ordering is correct, but Mendeleev had them backward if the atomic number ordering is correct. Or just question, why did elements exhibit periodic behavior? Remember, Mendeleev just grouped them together in terms of their periodic behavior, but why did they show that periodic behavior? A man named Henry Moseley helped to clarify some of these problems. Good old Hank Moseley, he was an English physicist who determined the number of positive charges in the nucleus, aka the number of protons, by measuring the wavelength of the X-rays given off by certain metals back in 1913. Okay, so this was the first time, okay, and realize we're talking some 50 years, 40 to 50 years after Mendeleev published his first periodic table. Finally, the techniques to measure the number of charges in the nucleus is coming out, right? So Mendeleev had no chance of using that data to construct his table. But here comes Moseley a little bit later, quite a bit later, and he developed a way to do just that, basically to be able to count the number of protons in a nucleus, therefore giving us access to atomic numbers. But he was killed by a sniper in Turkey during August of 1915 during World War I. Now, a lot of people assume that he was on his way to receiving the Nobel Prize for this. However, the Nobel Prizes, they are only awarded to people who are alive. Since Moseley had been killed in action, he was not able to receive that Nobel Prize. All right, so now we're moving on from this idea of arranging the periodic table in terms of atomic mass to arranging the periodic table in terms of atomic number. So here we go. X-ray experiments, right, by Moseley, revealed a way to determine the number of protons in the nucleus of an atom. It was known that there was such a thing as a proton, but there was no way to count how many of them were in the nucleus, which is, an important distinction there. It was found that the periodic table ought to be in periodic number order, not in atomic mass number. Okay, big distinction there, or at least a big difference in reason for ordering in that order. This explained the kind of tellurium iodine anomaly, in the sense that, well, iodine weighed less than tellurium, so it was listed first, but its chemical characteristics didn't match up perfectly in that order. Okay, so the chemical characteristics were a little bit off, but if we now order them in terms of atomic number, all of a sudden the characteristics line up perfectly. So this led to what's known as the periodic law. The periodic law states that the physical and chemical properties of the elements are periodic, remember, repeating in regular intervals, periodic functions of their atomic numbers. Just FYI, Moseley was killed in battle in 1915 during World War I. He was only 28 years old. There are some other bits of information that Mendeleev did not have while he was creating his table. There was even a few different categories of elements that had not yet been discovered at all. For example, the noble gases. And so we're going to start discovering the first noble gases around the time Mendeleev was publishing his first periodic table. Helium was discovered while studying the sun. Okay, emission spectra from the sun revealed this new, what must have been a new element, and they named it helium. And then we have William Ramsay going on a little bit of a bender, discovering argon, finding helium on Earth, not just in the sun, and then krypton and xenon. All this happened about 30 to 40 years after Mendeleev published his first periodic table. So in his first periodic table, the noble gases were completely unknown. To him, I should say, to Mendeleev. The other categories that were not known to Mendeleev, the lanthanides and actinides. Okay, in the early 1900s, again, well after Mendeleev had done his work, the elements from curium, which is number 58, to lutetium, number 71, they were separated, right, from one another, and they were identified. They were also called rare earth metals because they're less than 0.01% of naturally occurring elements. Also, the actinides, these elements need to be synthesized, basically. Things like thorium, number 90, all the way to lawrencium, number 103. Okay, these are exceedingly rare. In fact, they don't occur naturally. They have to be created, usually in some sort of particle accelerator. Now, both of these categories, both of these periods, lanthanides and actinides, they comprise the F block, right? We've already dealt with that, but they've been pulled out of the periodic table just for space reasons, okay? Just for space reasons. So this is how our modern periodic table is constructed, okay? We have our S block over here, okay? See, it's labeled here. Then we have the D block in the middle, most of the transition metals. And then we have the P block over here on the right, a big square. And then the bottom, we have the F block. But the thing is, these elements, the F block doesn't belong at the bottom of the periodic table. It actually belongs up here in between the S block and the D block. It actually truly belongs up here. And that's why don't we do that? Oh, for space reasons. Because if we put the F block where it belongs, your periodic table would be super, super wide and would be so small in order to fit on a piece of paper, you'd have difficulty reading it. Okay, so this is what it would look like. Notice that way down here, notice we have this nice increasing atomic number order. As you go from left to right, you are always increasing by 1 proton. And that looks good. We love patterns in science, and we love predictability in science. And to see these numbers go up by 1 in this nice smooth order, that's what we like. But in terms of printing, this isn't that easy. So the F block, the lanthanides and actinides, were taken out of the periodic table and placed underneath just for space reasons. But as we go through this section, in fact this entire unit, please feel free to refer to this periodic table from time to time so you can remind yourself exactly where the F block elements truly belong and why you go from 6s to 4f, then to 5d, and then to 6p, right? I'm just going straight across in an order, nice and ordered. So, what have we done in this lecture? We've explained the roles of Mendeleev and Moseley in the development of the periodic table. We've described the modern periodic table. We've tried to explain how the periodic law can be used to predict the physical and chemical properties of elements. And we've described how the elements belonging to a group in the periodic table are interrelated in terms of atomic number. All right, guys, that's it for this lecture. I will see you next period.